Hi. So welcome to the last talk for today. So the speaker is Bhargav Bhatt. Bhargav Bhatt, he got his PhD in 2020 from Princeton University, advised by Johan de Jong. And afterwards, he spent many years in Michigan in various positions as a postdoc, professor, and so on. And just this month, he has moved to the Institute for Advanced Study in Princeton University. For his work, he has won numerous prizes, including the Compositio Mathematica Prize. In 2015, a Packard Fellowship, and in 2021, he became a fellow of the AMS, and he won a Clay Research Award. Bhargav has actually been a frequent collaborator of mine, and actually checked, and the first email he sent me back in 2011 was asking whether one could use perfectoid techniques to prove something about cohomology of absolute integral closures, and I was like, I don't know nothing about this. I would be very surprised. And we collaborated on lots of other things. And then suddenly he was able to, 10 years later, prove this cohomology of absolute integral closures using perfectoid techniques and a lot of stuff that we've developed in the meantime. And I'm quite excited about that. And I think this is what we will also talk about today. So, Bhargav.
Okay, great. So I would like to begin by thanking the organizers for providing me this wonderful opportunity. It's a great pleasure and a great honor for me to be giving this talk. And so I would like to talk today about algebraic geometry in mixed characteristic. And more precisely, what I want to do is I want to talk about certain advances in algebraic geometry or in a p-adically complete setting that became possible by the advent of prismatic cohomology. And so the plan for this talk is that in the first half, I will tell you a little bit about the problems that motivated the discovery of prismatic cohomology and what it looks like. And then in the second half, I will try to explain certain applications of prismatic cohomology to a few different areas of mathematics where the p-adic numbers appear. Okay, so let's begin. So let me begin by formulating a certain motivating goal that that sort of informed the search for this cohomology theory. And so let me fix a prime number p once and for all for the entire talk. And let's begin in the last century, early in the last century. So in the 1930s, de Rham proved a theorem, and then Hodge improved it 10 years later. And it gives us a lot of insight into the structure of compact complex manifolds. So more precisely, let's say X is a compact complex manifold, which is scalar. A typical example, most certainly the one relevant for this talk, is when X is a closed subset of complex projective space, which is a complex submanifold. So it's something by Chow's lemma, this is always defined as by the zeros of a bunch of polynomials. So it's actually an algebraic variety. It's not just a random complex manifold. And in this setting, you can study X through various techniques. So you can, for example, put on your topologist hat and think of X just as a topological space and attach to it invariants like its fundamental group, singular homology, singular cohomology, and so on. You can also think about it more geometrically in terms of its differential structure and think about things like differential forms on the manifold. And you can go all the way and think about it from a complex geometric point of view. So using the Kähler structure, you might be able to think about the notion of harmonic forms on this manifold. And these theorems that I'm recalling make all of these structures talk to each other. And so here's one version of the statement. So there are three objects that are isomorphic to each other. So the left-hand side is the singular cohomology of X with complex coefficients. This is a purely topological invariant of X. It doesn't care about any of the additional structures that X possesses in this case. In the middle, we have the de Rham cohomology of X. So this is defined using the notion of differential forms on X. So this cares about the C infinity structure on X. But then in the presence of the Kähler structure, you can further decompose de Rham cohomology into a bunch of pieces. And so this is called the Hodge decomposition. This is the Hodge part of the theorem. And what it tells you is that Hn de Rham decomposes into a direct sum of Hij's, where I plus j equals n. And what are the Hij's? Well, they are the subspaces of de Rham cohomology spanned by forms that can locally be written in terms of I many dz's and j many dz bars. And so this clearly sort of cares about the complex structure of X. And then the fact that this is a decomposition is a non-trivial theorem. And so this is a theorem that gives you a connection between the topology of X and something having to do with its complex function theory. And you can use it in both directions. And so, I mean, this is a starting point of Hush theory, and I don't want to discuss Hush theory in this talk, but I thought I would at least give you a couple of examples of how you might use this theorem. And so let's first try to extract topological consequences from this theorem. And so here's a very easy one to observe. So let's say n is an odd integer. So I claim that in this case, the dimension of Hn always has to be even. And the reason for this is very simple. It's because these vector spaces Hij appearing on the right, they appear in complex conjugate pairs. Hij and Hji are isomorphic to each other via complex conjugation. And so in particular, their dimensions have to be the same. And now if you look at the i's and ij's, which sum up to n, when n is odd, they appear in pairs. And so the dimension it follows is a multiple of 2, and therefore it's an even number. So the reason is simply as Hij is Hij bar. Oops. Okay. Let me now try to explain an implication in the other direction. So let's say, for some reason, let's say you knew that X was simply connected. So its fundamental group was 0. So I claim in this case that there are no non-trivial holomorphic one forms on X. So all holomorphic one forms have to vanish. And one way to see this is to stare at this theorem for n equals 1. So H1 with C coefficients is going to be 0 because pi1 is 0. That's basic algebraic topology. And once H1 is 0, you know that the two summands that contributed to the right on the right also have to be 0. So H01 and H10, they both have to be 0. But what is H10? Well, it's exactly the space of global holomorphic one forms if you think in terms of the local description I mentioned earlier. And so therefore, it follows that H10 has to be 0 because it's a subspace of 0. And so this is an example where you make a topological assumption and you get a geometric consequence. And so you see, you can use this in both directions. And it's a wonderful theorem. This talk, however, starts off with, if you like, a defect of this theorem. And the defect is that this process of forming singular cohomology with C coefficients it ignores all the torsion information. So really, singular cohomology was defined with Z coefficients, and then you're supposed to tensor up with C to get the version with C coefficients. But the process of tensoring from Z to C completely destroys all the torsion. And so if you want to see torsion information in the picture, this is not going to help you very much. And so essentially, the goal of this talk is to explain how to fix this, or one recent approach towards fixing this. And since, and before maybe I formulate it that way, let me just make one simplification. So this is a finitely generated abelian group. And so its torsion decomposes into a direct sum of p primary components, one for each prime p. And so we might as well just focus attention on one of those components. That's my fixed prime number p at the start of the talk. So that's the first simplification. And then the second one is that by universal coefficients theorem, essentially understanding the p torsion in the cohomology of X is the same as understanding its mod p to the n cohomology. And so let me formulate a goal now, which I would like to spend the rest of this talk explaining. So the goal is to understand the cohomology of X with z mod p to the n coefficients in some geometric fashion. And so by geometric fashion, I mean something similar to what's happening over here, i.e. in terms of differential forms. And as stated, this goal is unrealistic, or at least I don't know how to make it true in this setting. But at least when X is an algebraic variety, we'll see some partial results towards this. So that's the plan. And what I would like to do now is to sort of explain a setting in which these structures can talk to each other. So first of all, if you want to understand mod p to the n objects, like the singular cohomology of X with z mod p to the n coefficients, in terms of differential forms, we need to be understanding differential forms also in a mod p to the n setting. So we cannot think about differential forms in Kirsig 0. We really should be thinking about differential forms in Kirsig p. On the other hand, we still want to understand the mod p cohomology of our original complex manifold X. And so we don't want to forget about Kirsig 0. And so we want to be in some setting where the two characteristics can talk to each other. And that's what I want to explain next. So this is the p-adic world. This was discovered by Hensel in 1897. And let me just introduce some basic objects. at play. So ZP is going to be our notation for the ring of p-adic integers. It can be defined in various ways. One easy way to think about it is that it's a completion of the ring of integers with respect to a certain metric, the p-adic metric. And in the p-adic metric, two integers are close to each other if their difference is divisible by a big power of p. So for example, 2 is smaller than 1 in the 2-adic metric because 2 is closer to 2. And 4 is smaller than 2, etc. A more sort of analytic way of thinking about it is as some kind of formal power series. And this was, in fact, I believe, Hensel's motivation for introducing this object. So you can think of it as formal power series where somehow the variable of the power series is now p. And the coefficients are drawn from the 0 through p minus 1. So sort of if you squint a little bit, it sort of looks like it was formal power series in a variable p. Of course, this doesn't really make any sense. But that's kind of what it looks like. Here's a picture maybe that helps explain better what the p-adics look like. So this is an illustration of Z3. So P is 3 over here. And as I was saying, elements are close to each other if they're going to be divisible by high powers of 3. So the outer ball is all of Z3. The inner balls, 3 yellow balls, they correspond to the 3 congruence classes mod 3. So everything that's congruent to 0 mod 3 is over here. Everything congruent to 1 mod 3 is over here. And 2 mod 3 is over here. And then within the things which are congruent to 0 mod 3, you can further partition into in terms of congruences mod 9. So this is 0 mod 9, this is 3 mod 9, this is 6 mod 9. And then, okay, you can imagine you can keep going further and further. This is congruences mod 27, etc. And so the p-adic numbers have this kind of a fractally nature. And this fractally property of the p-adic numbers is going to sort of lurk in the background throughout this talk. It's not going to come up very much explicitly, but it's certainly there in the background. What's going to come up much more explicitly for us is a certain algebraic property of the p-adic numbers. And so the algebraic property is the following. You take this ring, ZP, it's a ring. You can do 2 things to it. You can either sort of set p equal to 0, so you can kill the ideal generated by p. And what you get then is the finite field fp. On the other hand, you can also invert p. And when you invert p, what you get is a field. So this is called the field of p-adic numbers. And this field is the p-adic analog of the real numbers. Just like the rational numbers completed for the standard metric give you R, if you complete them for the p-adic metric, they would give you QP. And then just like you go from the real numbers to the complex numbers, you can do something similar here. So you can go to the algebraic closure. The algebraic closure in this case is not complete because this is an infinite degree extension. And so you also have to complete it. And so when you complete it, you get what is typically denoted by CP. This is the p-adic complex numbers. And lest this feel like a very exotic construction, let me just point out that if you make certain non-canonical choices and assume the axiom of choice, the field CP is actually isomorphic to the usual field of complex numbers. So it's not a new object. It's just it's an old object presented in a very complicated fashion, which is more adapted to thinking about p-torsion phenomena. But we're not going to really be using this except for motivational purposes. And so one way to summarize all this stuff is to say that ZP provides some kind of a bridge from characteristic 0, namely CP, to characteristic P, namely FP. And we're going to be using this bridge to relate objects in characteristic 0 with objects in characteristic P. Okay, and so that's kind of the base we're going to be working over. And then the geometric object I'm going to call X. So X is a smooth projective variety over ZP, meaning it's defined by polynomials with coefficients in ZP inside projective space. And then there's a non-degeneracy condition corresponding to smoothness. And so since ZP is a ring, let me sort of just highlight some observables you can extract out of this. So we have a bunch of equations with coefficients in ZP, and we can just regard those equations as having coefficients in CP via this embedding. And if you do that, then the resulting object, XCP, is a smooth projective variety now over this field CP over the p-adic complex numbers. So it's the kind of object we want to understand. If you like, if you use such a non-canonical isomorphism, it's a compact complex scalar manifold. But you can also do the same maneuver. Instead of going along this arrow, you go along this arrow. So you can go to characteristic P. And so XFP is going to be the corresponding smooth projective variety you obtain over the field FP. And so attached to this data X, we have two geometric objects. One is this characteristic 0 variety XCP, and one is this characteristic P variety XFP. And this is going to be some kind of a characteristic P partner to this characteristic 0 object. And this is where the sort of differential information is going to be living. And this is where the topological information is going to be living. Okay, I was jumping a little ahead of myself. So let me give you an example of what these things could look like. So here's the example of a Fermat cubic. So this is the 0 locus of x cubed plus y cubed plus z cubed. It's a homogeneous polynomial in 3 variables. So you can think of its zeros as living inside projective 2 space, P2. And if I assume P is not equal to 3, then what I have is a smooth projective variety over ZP. And here's a picture for what it looks like. So X is this box. It lives over spec ZP, which is just the algebraic geometer's notation for saying that the coefficients are coming from ZP. And you can think of it as being sort of comprised of these two objects, XCP and XFP. XCP is a Riemann surface of genus 1. It's an elliptic curve. And similarly, XFP is an elliptic curve. This one is in characteristic P, and this one is in characteristic 0. And the fact that you have this X relating them gives you a rather close connection between XCP and XFP. And this is typically what these examples look like. So you have some characteristic 0 variety, and then you have some characteristic P partner. And to a first approximation, you can think of them as sitting in some kind of a nice family. It's a submersion over some base. It's just that the base happens to be of an arithmetic nature rather than a geometric nature. Okay, so that was the geometric setting. And now let me go back to this question I had before. So I mentioned that our motivating goal is to understand the mod p to the n cohomology of a characteristic 0 variety. And so let's again fix our notation. So x over zp is a smooth projective variety. So we have xcp and xfp, these two varieties over these two fields. And a principle that emerged in the second half of the last century, more precisely in some calculations of Tate, followed by their reinterpretation by Grothendieck, and then more precise conjectures formulated by Fontaine, was the following. So it said that if you are trying to understand the mod p to the n topology of XCP, so this is a loose phrase. I mean things like the mod p to the n cohomology of X, or homotopy if you want to be fancier. XCP should be closely related to the algebraic geometry of this characteristic P variety, XFP. So things like, differential forms or the tangent bundle and so on this characteristic P variety, XFP. And this is an approximate symbol, meaning there's not any assertion to the effect that, the sum equivalence of categories or anything like this, but it's a principle. And it was a principle that was sort of witnessed first, I think, in some examples of abelian varieties coming from Tate. It was noticed by Grothendieck, and then Fontaine formulated some rather precise conjectures about how such a relationship, the shape of such a relationship. And so what we learned by the end of the last century through the work of a ton of people was basically that this principle works extremely well if you ignore p-torsion phenomena. So ignoring p-torsion phenomenon is orthogonal to what we actually want to do, but it's important that I explain what happens first in a simpler setting before we get to the fancier one. And so here's a result of Faltings and Tsuji basically justifying the statement over here. And so I will state it in a very, very loose fashion. It's not a precise statement because I'm just trying to give you a flavor for what's going on. But here's what it says. So let's say you're trying to understand the cohomology of XCP with ZP coefficients, so with p-adic coefficients now. So this is essentially, you look at, its focus is zooming in on the p primary part of the cohomology of the integral cohomology of XCP. And what the result says is that you can understand this at least up to isogeny, meaning up to bounded p powers, in terms of some rather complicated functor, which we don't want to discuss, applied to this characteristic P variety, XFP, together with some linear algebra data. So this fx is some kind of a linear algebra data. It's like a filtration attached to this choice of lift x of XFP. So ignoring this kind of subtlety over here, what this is saying is that there's some way to recover this invariant of the characteristic 0 variety in terms of something happening on the characteristic P variety. And this result, when precisely formulated, is extremely useful, and you can use it in both directions. And so in the last century, there were several applications of this. So I'll just sort of summarize two of them in some very broad sense. And so the first one is to the Langlands program. More precisely, it's to the structure of p-adic Galois representations. And so what happens is that if your variety X is defined with coefficients, well, it's over QP, as I've been discussing, then this object over here has an action of the Galois group of QP bar over QP. So the absolute Galois group of QP. And so therefore it provides an example of a p-adic Galois representation of the absolute Galois group of QP. And such objects are the subject of the Langlands program. And the fact that you can understand such objects in terms of this data over here gives you new insight into the structure of these objects. And that's how this relationship gets used in this area. So that's an example where you can sort of use something you know about the right-hand side to conclude something you want about the left-hand side. You can also go in the other direction. So there's a rather famous result by Ito observing that the Hodge numbers of Calabi-Yau varieties in over the complex numbers are birational invariants. And the way, so the result is originally due to Kontsevich, and Ito gave a p-adic proof of it. And the way this argument goes is that you first prove something about this side, and then because you have this relationship, you get to conclude something about this side. In particular, you get to conclude something about the filtration data, which then lets you conclude something about the Hodge numbers. So at some very rough level, it's sort of using information on the Galois theoretic side to conclude results on the geometric side. And so the result can be used in both directions. Of course, it has a problem as far as our original goal is concerned, which is that it's completely throwing out the p-torsion information. And so now let me explain how modern methods allow us to fix this. So what did we learn in the current century? There's this new theory called prismatic cohomology, which gives you a relationship between the cohomology of XCP and XFP. And let me just state a theorem about it, and then we'll spend more time unraveling it. So what the result says is that whenever you have this smooth projective variety X as before, so X, let me write over here. So X over ZP is smooth projective. To this data, you can attach an invariant, which is denoted H star sub prism of X comma FP, which is a finitely generated module over FPT. So it's a cohomology theory taking values in finitely generated modules over this ring FPT rather than over a field. This is not a very exotic ring. It's a PID. It's a pretty nice PID. And this cohomology theory has two features that I want to emphasize. So the first of those is a topological comparison, which says that if you invert this parameter t that's showing up, then this theory is something we already knew about. Namely, it's the singular cohomology with FP coefficients of the scarcely zero variety, and then brutally scalar extended from FP to FPT. So this operation doesn't really do anything. So what this is saying is that after you invert t, all the information is already just the information you had before in singular cohomology with mod p coefficients. But something interesting happens when you mod out by t. So there's a differential comparison that says that if you take prismatic cohomology, sorry, I guess I didn't say this, but this cohomology theory is called prismatic cohomology. I hope that was kind of obvious by what I've been saying before. But anyways, so if you take prismatic cohomology with mod p coefficients and you reduce it mod t, what you get is the de Rham cohomology, not singular, but the de Rham cohomology of the scarcely p variety, XFP. And so the theorem, basically what this is saying is that this cohomology theory gives you some kind of a relationship between singular cohomology with mod p coefficients and de Rham cohomology of a scarcely p variety. And that's exactly the kind of relationship I was alluding to at the start of the talk. And so let me make a few remarks about this theorem and maybe unravel it a little bit more. So first of all, I should say that at least some partial inspiration for this theorem was in the work of Breuer and Kissin on Galois representations. Essentially, in a non-geometric context, purely in some Galois theoretic context, they took objects like this and outputted objects that look like this. It wasn't quite literally the same objects, but certainly the construction was close enough to suggest that there should be such a cohomology theory. The second remark I want to make is that as a consequence of the theorem. So if you just take this theorem and sort of do some basic linear algebra, what you get to conclude is that the dimension of this vector space over here, so the mod p cohomology of your characteristic zero variety, is bounded above by the dimension of the de Rham cohomology of your characteristic p variety. And so what this is saying is that there is some procedure, possibly indirect, to take a mod p cohomology class on X, the kind of object we want to understand, and translate it to a differential form. But now the differential form lives on X in characteristic p rather than on X in characteristic zero. So it's some version of the de Rham comparison, except in this weird setting. And it's not as good as what happens in characteristic zero, in that we are just saying there's an inequality. We're not saying it's inequality, and there's a good reason for that. It's because there are examples showing it cannot be an inequality. So in this is the best you can do with these methods, and in some sense there's a reason for that. So you cannot actually hope to have an equality over here. But in any case, this gives you the promised relationship between mod p cohomology classes in characteristic zero and some kind of differential forms in characteristic p. And in the rest of the talk, I'll sort of try and give some applications of this as we go along. But let me continue making remarks first. So maybe another thing to say is that, as the notation suggests, this cohomology theory, I had an FB over here to indicate that this was the version with mod p coefficients. Of course, there's a version with integral coefficients. So there's a ZP version, which now takes values in modules over ZP joint T rather than over FP joint T. And in some sense, this has a little more information. And so I wanted to actually tell you a picture what this looks like. And so here's a picture of this module, prismatic cohomology with ZP coefficients over ZP joint T. And so what I'm thinking over here is in terms of linear algebra. So if you have a vector space or with two commuting operators acting on it, you can sort of you can think of the vector space as living on the plane. And it's some kind of a generalized bundle living on the plane. And then the fiber of this bundle at the point little a comma little b is the simultaneous eigenspace where the first variable acts by a and the second variable acts by b. So it's some kind of an eigenvalue spectrum of this vector space. And so we can do the same thing in this p-adic setting. So you can think about the spectrum of this ring as some kind of a two-dimensional object. And then this module can be thought of as some kind of a generalized bundle living on this two-dimensional object. And what I've drawn over here are the fibers of that. And so something, let's just go through this from left to the right. So if you restrict this generalized bundle to the to the y-axis, so to the vertical axis, which is t equals 0, what you recover is a cohomology theory we already knew about called crystalline cohomology. So this was something constructed by Berthelot in his thesis. If you move a little bit to the right and you sort of restrict attention to t equals p to the p, what you get is de Rham cohomology, not of the characteristic p variety, but rather of the full variety X itself. So over here, you would have de Rham cohomology of the characteristic p variety, but then as you move along over here, you have the de Rham cohomology of X itself. And then in general, in the yellow part of the picture, this invariant that we are defining essentially had some kind of a classical description. So one way to say it is that it's what was called the A-Cris cohomology. But then something interesting happens when you move to the blue part of the picture. So the first observable there is what happens along the diagonal itself. So if you look at t equals p, which is the diagonal, you get a cohomology theory which seems to be new. So we're calling it Hodge-Tate cohomology, and it seems to be a rather useful invariant of this variety X. And then there's new stuff here. And then what happens along the x-axis is exactly what the theorem was about. So in the theorem, I was telling you what the shape of prismatic cohomology with mod p coefficients. And working mod p is the same as working on the x-axis, because p is equal to 0 is what defines the x-axis. And so what the theorem says is that if you sort of are on the x-axis and you're away from 0, so if you're in this part of the picture, if you're in this part of the picture, then what you get is mod p étale or singular cohomology of the characteristic 0 variety, XCP. But then when you get closer and closer to 0, something interesting happens. And at 0, you're not going to get étale cohomology, but rather you're going to see de Rham cohomology. So all the action is sort of localized in this part of the picture. And that's where this theory is providing something new. And so this is roughly what prismatic cohomology looks like. It's some kind of a way to interpolate between various cohomology theories that we knew about And the fact that you can interpolate between them gives you some relationships between them. Okay. So that was about the integral variant. And then I also wanted to say that for applications, it's more useful to have a semi-stable variant. So semi-stable refers to the fact that in the setup I was talking about, my x was assumed to be smooth over ZP. So it was like a submersion over ZP. Both XCP and the characteristic P fiber XFP were assumed to be smooth. And for certain applications, it's too strong to assume that the characteristic P fiber is also smooth. You want to allow some kind of singularities on the characteristic P fiber. And the ones which are sort of reasonable to allow and are yet tractable enough to work with are called semi-stable. And so this theory was extended to the semi-stable setting by Chesnavikus and Koshikawa, and then Koshikawa. And I don't want to sort of tell you what semi-stable reduction is, but maybe I'll explain it with a picture. So here's an example of a genus 2 curve with semi-stable reduction. Here's a perfectly nice genus 2 surface over the p-adic complex numbers. And then when you start reducing mod p, and what happens is that you had this cycle over here, which got collapsed. So it vanished when you went to the special fiber. And so now in characteristic P, what you have is not quite smooth because it has one singularity at the origin. But it's a pretty tame object, and one can still work with it. Okay, and then the final remark I want to make about the abstract structure of prismatic cohomology is a historical one. So I want to tell you a little bit about how, or what the constructions are. So there are a few different constructions of this cohomology theory one can give now. The very first one was an analytic one, which was through the theory of perfectoid spaces. That's what this 2016 paper referenced over here is doing. It crucially relied on what's called the Falting's almost purity theorem. The second one, which is more homotopical in nature, so it's connected to algebraic topology, comes from algebraic K-theory and topological Hochschild homology. So I will talk about this in a few minutes. So let me not spend time on it right now. The third one, which is a purely algebraic one, is via the notion of a prism, and that's where the name comes from. The name prismatic cohomology comes from here. In some sense, this is the most flexible one of the ones I've discussed so far, and it is also more useful or more elementary because it's purely algebraic. And finally, in the last couple of years, there has also been a sort of a revisiting of the purely algebraic construction, which sort of made it more algebra geometric. It was through the techniques of derived algebraic geometry, and it was discovered independently by Drinfeld and also myself and Jacob Lurie. And I'll come back to this later and towards the end of the talk. But what I want to do next is I want to talk about some applications of prismatic cohomology. So far I've told you what the motivating goal was, which is relating differential forms in characteristic 0, relating mod p cohomology classes in characteristic 0 with differential forms in characteristic p. And then I also told you about this cohomology theory, which exactly gives you such a relationship. And so now let's see how one might go about using this. And so what are the kind of applications that you can get once you know about the existence of such a cohomology theory? So for my first application, I want to talk about connections with algebraic topology, and more precisely connections with algebraic K-theory. And so before getting to algebraic K-theory, let's talk for a little bit about topological K-theory, because that's where the motivation for this application comes from. So remember, if X is a nice topological space, then one can attach to it a generalized cohomology theory, K of X, which is the K-theory, and it's a complex K-theory of X, and it's built out of the notion of complex vector bundles on X. This was defined by Atiyah Herzebruch based on Bott periodicity about 50 years ago. And it's played an important role in algebraic topology. In particular, it's played an important role in the solution of various interesting geometric problems through methods of algebraic topology. And not only did Atiyah Herzebruch construct complex K-theory, but they actually gave us a recipe for computing complex K-theory in terms of simpler objects, namely in terms of singular cohomology. And so let me recall what they proved in the form of the following statement. So this is, as I said, it's a combination of the Atiyah Herzebruch spectral sequence and the Bott periodicity theorem, and here's a way to state it. So it says that for a nice topological space X, there's a natural filtration, which I'll call the skeletal filtration, on its complex K-theory, on this generalized cohomology theory, And the associated graded pieces of this filtration are just given by singular cohomology with some decorations. And so the first decoration over here is a Tate twist, and you can essentially ignore it at first pass, not much is lost. And the second decoration is 2i, so that's just a cohomological shift. And so this is some rather fancy way of stating that there exists an Atiyah-Hirzebruch spectral sequence, which computes complex K-theory groups and at its E-infinity page and starts off with singular cohomology groups at the E2 page. So this is an extremely important computational result in algebraic topology, and it is natural to search for a version of this result in pure algebra or in algebraic geometry. And so the first question one meets there is that if X is now an algebraic variety, then what even is the notion of K of X? And then once you have an optimal answer to this question, you can search for an optimal answer or an optimal analog of this theorem. And so the first of those questions was answered in the 70s. So after a period of intense activity following this result over here, in 1973, Quillen gave what's now considered the definitive notion of higher K-theory, or algebraic K-theory. So this is for an algebraic variety X, Quillen K-theory is a generalized cohomology theory attached to X. And it's built from the notion of algebraic vector bundles on X, as opposed to complex vector bundles that were showing up in the topological analog. So this is very closely related to things like line bundles on an algebraic variety and higher rank generalizations thereof. In the period since the 70s, algebraic K-theory has played an extremely important role in various parts of algebraic geometry. In particular, it features prominently in some of the deepest conjectures in arithmetic geometry. So it is an important invariant that we would like to understand better. The problem is that it's rather difficult to compute it, even for very simple examples. And so it would be nice if there was an analog of this theorem that at least gave you some kind of a computational tool for computing algebraic K-theory. And so this question was posed explicitly in 1982 in the work of in Bailenson's rather influential work on the theory of mixed motivic sheaves. And he asked, what is the analog for algebraic K-theory of a variety X or a ring R off the Atiyah-Hirzebruch-Bhatt theorem over here? And so this question generated a lot of activity. And Bailenson himself, I mean, it wasn't just this question as written over here. Rather, he gave some precise guesses for what the filtration could look like and what the associated graded pieces could look like and what their structure exactly is. And his conjecture was proven away from the characteristic of the ground field in the last century, essentially. So I'll state it this way. So the rational/l-adic case was mostly answered in the 20th century. It was answered in the work that emanated from motivic homotopy theory. And essentially, it says that if you allow yourself to rationalize, meaning you ignore torsion information, or l-adically complete, meaning you complete at a prime L, which is different from the characteristic of the field you're working over, then there exists a nice filtration on algebraic K-theory, and the associated graded in that case is something called motivic cohomology, which has an independent definition. And this provides you a rather useful tool for computing, or at least trying to compute algebraic K-theory. And so this was through the work of a lot of people, and I just listed some of the relevant names here. And so in some sense, if you're interested in this question, the key remaining case is the p-adic case, meaning you work with algebraic varieties over a field where P is not invertible, or over a ring where P is not invertible, such as ZP, as we had been doing. And you only care about the p-adic information in algebraic K-theory. What is the analog of the statement over here then? And so this is what I would like to explain. And so here's a theorem that was proven in the last few years, but it really builds on a lot of previous work in the area. And I'll just state it and then we can go over it. So I will state it in algebra instead of for algebraic varieties. So for any p-adically complete commutative ring R, for example, R could be any commutative ring where some power of P is 0. So P nilpotent ring is an example of a p-adically complete ring. And what it says is that for such a ring R, there is a natural filtration, which we call the motivic filtration in analogy with what happens over here. And this motivic filtration is a filtration on K-theory, slightly modified in a way I'll describe in a second, with the property that the associated graded pieces are described in terms of some objects that, at least at the level of symbols, look similar to what was showing up in the Atiyah-Hirzebruch-Bott theorem. Okay, so that's the statement, and now let's actually make sense of some of the terms. So the ZP over here indicates I have p-adically completed, so I only care about the p-adic information. Étale refers to étale sheafification, so this is a slight modification of the algebraic K-theory, which tends to make it more computable. And in general, étale sheafification can be quite a drastic operation which changes the theory significantly. But if you're working in a p-adic setting, like I am, where the ring is p-adically complete, then somehow étale sheafification is relatively mild. It's under control. And so this is not that different from just the usual algebraic K-theory. And this is the invariant I want to say something about. One can say something about the non-étale sheafified version, but I will not do that in this talk. So this is our sort of the version of K-theory that we are trying to understand. And the theorem is saying that there is a way to compute it in terms of this object over here. So what is this object? This object is called symptomic cohomology. So it's a new cohomology theory attached to this ring R. And where does it come from? It actually comes from prismatic cohomology. So this is a cohomology theory that is defined in terms of prismatic cohomology. And at some very coarse level, the way you obtain it is by observing that prismatic cohomology carries a certain natural operator on it. And this cohomology theory is a certain eigenspace of that operator. So there's a precise definition, but that's kind of the idea. And so what this theorem is saying is that there is a way to compute algebraic K-theory, étale sheafified in this p-adic world, in terms of symptomic cohomology. And so we now have a tool for computing étale K-theory similar to what the one provided by Atiyah, Hirzebruch, and Bhatt for usual topological K-theory. And so on the next slide, I want to explain some sort of more concrete calculations that come out of this theorem. But maybe before I go on, I should say that this theorem was not proven in a vacuum. So as I said, there's a lot of work, previous work in the area. The story really starts with some work in the 90s by Buckstedt, Xiang, and Madsen on the K-theoretic analog of the Novikov conjecture. And they pioneered the use of what's now called trace methods to compute algebraic K-theory. And essentially, these trace methods allow you to compute K-theory, algebraic K-theory, in terms of some other invariant called topological cyclic homology. And the way this theorem is proven is by proving some analogous statements for topological cyclic homology. And so there's really a lot of work of a lot of people that sort of goes into proving this theorem, and I'm only telling you the final statement. Okay, great. So now let's see some calculations that one gets out of this approach. So as I said, the theorem gives you a tool for computing K-theory. And now that we know that prismatic cohomology, and therefore symptomic cohomology, has this purely algebraic definition that I mentioned 2 slides ago, it follows that using this theorem, we actually get a new tool for computing K-theory. And this turns out to actually be a useful thing to do. So here are 2 calculations I wanted to discuss. So let's fix an integer n, which is at least 1. The first theorem I want to discuss is what we call the odd vanishing theorem. This is some kind of a p-adic analog of a part of Bhatt periodicity. So the Bhatt periodicity theorem in topology tells you that if you look at a reasonable topological space and you think about its complex K-theory, then locally on the space, this invariant is concentrated in odd degrees, simply because locally the space is contractible, and K-theory of a contractible space is the K-theory of a point. And the K-theory of a point by Bhatt periodicity lives only in even degrees. So locally, you have some odd vanishing, vanishing in odd degrees, and that's the version of the theorem that generalizes to the algebraic setting. And so the odd vanishing theorem states the following. I'm stating it very roughly. It says that the odd degree K-theory groups of R with p-adic coefficients vanish if R is sort of really large. And I'm not going to be able to make precise in this talk what very large means, but I will content myself by presenting just one explicit example of the kind of ring to which this applies. So if you remember the p-adic complex numbers CP, they were defined as the completion of the algebraic closure of QP. QP had a p-adic metric on it, and this p-adic metric passes through this process to give you a p-adic metric on CP. And its ring of integers, OCP, is a valuation ring, which is like an extension of ZP. And so you can take that ring and reduce it mod p to the n. And then the odd vanishing theorem implies that the odd K-theory of this ring vanishes for any integer n bigger than or equal to 1. And so this theorem was previously inaccessible, or was previously accessible when n was 1. So if you just work with OCP mod p, the point is that in that case, the ring is an FP algebra. So it's an algebra that contains a field because p is 0. And for algebras that contained a field, there were previously some other calculations that were available that one could use to deduce this vanishing over here. But if you allow yourself to pick n bigger than 1, so for example, n equals 2, then this ring over here does not contain a field. And these tools that were available for rings containing a field are completely useless. And so you need some new input over here. And the new input comes exactly from the theory of prismatic cohomology. More precisely, there's a local way to compute prismatic cohomology in terms of what's called Q-de-Rham complexes. That's one ingredient that goes into this. And the other one that I wanted to mention is flatness lemma proven by Yves André. So Yves André proved the direct summand conjecture, which was a really important conjecture in commutative algebra a few years ago, using perfectoid methods. One of the sort of key innovations in his approach was this flatness lemma for perfectoid spaces. This flatness lemma has a prismatic incarnation, and this prismatic incarnation is what you really need in order to carry out this calculation. So there's this rather pleasant interaction that's happening between sort of problems that originally originated in commutative algebra, going back to calculations that are more relevant in algebraic topology. Okay, so that was the first calculation I wanted to mention. And then the second calculation I wanted to mention was an even vanishing theorem. So this is extremely recent. It's from just a couple of months ago. It's by Antio, Krause, and Nicolas. And it concerns the K-theory of an extremely simple ring. So it's Z mod p to the n. So if you work with Z mod p to the n and you look at its algebraic K-theory in even degrees, then their theorem says that it vanishes provided the degree is sufficiently large. In fact, you can be more precise about how, like, they have bounds on how big K needs to be in terms of n. And so I think this is an amazing result because previously we had no tools for computing something like the K-theory of Z mod 4 in arbitrarily high degrees. And they really sort of tell us what it looks like in even degrees. And moreover, their theorem is sharper than this. It actually gives an algorithm to compute K-theory in any degree. And so it's really nice. And sort of the new input that goes into their theorem is, well, they use this filtration that I mentioned on the previous page in terms of prismatic cohomology, but then they also observe some new phenomenon about prismatic cohomology that sort of fall under the general umbrella of absolute prismatic cohomology, which is a topic I will not be discussing in this talk. And so, yeah, I think these are the two calculations I wanted to mention. As I said, as I write over here, and as I said before, both these calculations were out of reach for n bigger than 1. And the proof crucially passes through this equivalence, this filtration in terms of symptomic cohomology, and then at the end ends up being about calculations in symptomic cohomology. Okay, great. So that was the first application I wanted to mention. The second application I wanted to mention is in algebraic geometry. So this is the Kodaira vanishing theorem in mixed characteristic. And so before we talk about the Kodaira vanishing theorem in mixed characteristic, let me first recall what the Kodaira vanishing theorem in just classical settings is. And it's the following statement. It's a result of Kodaira. It's from the 50s, and it's an extremely important result in complex algebraic geometry. Here's one version of it. So if I give you a smooth projective variety of dimension d over the complex numbers, so a complex submanifold of projective space of dimension d, then what the theorem says is that the cohomology of the negative twist of the tautological bundle, so O of -1, has a lot of vanishing. Namely, it vanishes in every degree except the top degree being the dimension in this case. So this is, if you like, a vanishing theorem in coherent cohomology. It's a purely algebraic statement, and you can, if you're given defining equations that define the variety, you can write down what these groups are in terms of those defining equations rather directly. So there's nothing kind of topological going on over here. This is an algebraic statement. I've formulated it over the complex numbers, but once you have it over the complex numbers, you immediately get it over any field of Kirsig 0 by something called the Lefschetz principle. And this is basically because it's a statement in pure algebra. It involves finitely many equations with finitely many coefficients, and so somehow it doesn't care about how big the ground field is. But it does not apply to characteristic P. So if you replace your field C with FP, it certainly doesn't follow. You don't get to deduce anything from this theorem. And in fact, it turns out that the vanishing is actually false if you're in those settings. So if you're outside of Kirsig 0, then the Kodaira vanishing theorem is stated over here as false. And so Raynaud gave examples for smooth projective varieties over a field of characteristic P for which this vanishing fails. And then Totaro very recently gave examples of objects in mixed characteristic, so objects over ZP, where the analogous vanishing also fails. So in some sense, if you like, that's the end of the story. But of course, we want some positive results. We want to know how to actually, if this can be fixed. And it turns out that there is actually a pretty reasonable way to fix it, which is you allow yourself to work up to finite covers. And so what I mean over here is the following. So this was a theorem from a couple of years ago. And the statement is going to be similar to the one above, except you only have a vanishing up to finite covers. So X is a projective variety of relative dimension D over the p-adic integers, ZP, as before. And then what the theorem says is that there exists a finite cover, pi, from Y to X, such that the classes that you want to be zero, if Kodaira vanishing were true, become zero when you map them to Y, when you pull them back to Y along this map pi. So it is not saying that this group over here is zero. It is also not saying that this group over here is zero. But the classes that you encounter that shouldn't have been there on the left-hand side die when you pull them back to the right-hand side. So in some sense, you can never there are examples showing that you can never actually find a finite cover for which this group over here vanishes. So the stronger form of the statement that one could hope for, that maybe Kodaira vanishing is literally true for a finite cover of X, is not true. However, what is true is that any class that you meet can be annihilated when you pull it back to a finite cover. Let me just make one further comment before I go on, which is that the finite cover Y over here is definitely ramified. So you cannot do this with unramified covers. You really need to allow ramification. It's crucial to the method of the argument, and there are examples showing that it is even necessary. So this is the version of Kodaira vanishing that we do have in mixed characteristic. And I will discuss a few applications of it, but let me first make some remarks on it. So first of all, this formulation or this idea of working up to finite covers, it's very nice, but it's not actually new. It goes back to the work of Hochster, Hunicke, and Karen Smith from the early 90s. And essentially, they proved the version of this statement where ZP is replaced with FP. So they proved the analog of this theorem over a field of characteristic P rather than over this ring of mixed characteristic. And when you're working in characteristic P, meaning when P is zero in the ground ring, there are a lot of more tools available, tools like the Frobenius endomorphism, which are not available anymore when you pass to ZP. Great, so that was the first comment. And then the second comment I wanted to make was, right, so maybe at this point, you might actually be wondering, what does this theorem, which is a statement in pure algebra, have to do with prismatic cohomology? After all, the only p-adic thing showing up on this entire page is this ground ring ZP over here, but everything else is a statement in pure algebra. These cohomology groups have nothing to do with anything p-adic. They're just purely algebraic constructions. And so it comes in the proof. And the way to sort of at least motivate this conceptually is that if you want to prove the Kodaira vanishing theorem in complex geometry, probably the most efficient way of proving it is to first translate this using classical Hodge theory into a statement in topology. And then the statement in topology, you can prove using other arguments. And so the precise statement I have in mind is you can reduce this using Hodge theory to what's called the Andreotti-Frankel or the Artin vanishing theorem for affine varieties. So there's some Hodge theory that goes into proving the Kodaira vanishing theorem, and therefore it should not be surprising that you need some p-adic analog of Hodge theory to do something similar in mixed characteristic. And sure enough, one of the ingredients is indeed prismatic cohomology, which is why I'm talking about it today. And another ingredient that goes in is a Riemann-Hilbert construction for perverse sheaves on varieties in characteristic zero. And so usual Riemann-Hilbert machinery applies to constructible sheaves of complex vector spaces on a complex variety, but you might wonder what you can do with mod constructible sheaves of mod P vector spaces on a complex variety. And essentially, you can sort of see them in terms of sort of coherent objects living in mixed characteristic. That's what this work mentioned over here ends up telling you. And so I don't want to spend more time on the proof, but I wanted to tell you a little bit about some applications of this theorem, or some variants applications. So first, let me talk about a local variant of Kodaira vanishing. So the local variant is probably best motivated using a picture. And And so I'm trying to explain what I mean by the phrase local variant. And so this is just a general principle in projective geometry. Whenever you have a projective variety, let's say X and Pn, what you can do is you can sort of contemplate the total space of a line bundle on it, namely the inverse of the tautological bundle. So total space of O of -1. And the choice of -1 over here ensures that the zero section of this bundle is actually contractible in the sense that there's a birational map that contracts it exactly to the origin over here and does nothing else. And this is an affine variety, and in fact, it's the affine cone on X in projective space. And so you get this this correspondence, or this picture that relates a projective variety X to this affine variety, which is the affine cone. And on the affine cone, sort of all the information, all the interesting information is localized near zero, because if you zoom in pretty close to zero, since it's a cone, it looks more or less the same. And so the principle that comes out of this is that the projective geometry of X and Pn is very closely related to the local geometry of this cone at zero. This principle shows up in various kinds of geometry. In algebra, in algebraic geometry, it probably goes back to Serre's work on coherent sheaves in algebraic geometry. It's relevant for us is that it tells us that if you have a certain vanishing theorem on concerning the cohomology of projective varieties, that translates to a certain vanishing theorem concerning the cohomology or certain kinds of cohomology of this affine variety. And then you might hope that it's not actually special to this particular affine variety. In fact, it applies to any affine variety. And so that's actually what happens over here. So the geometric setup is going to be the following. So I'm going to fix a finite extension R of the p-adic integers. And so R is going to be the ring of functions on the affine variety we care about. Since I'm doing affines, I can make the statement entirely in algebra. I don't have to sort of talk about varieties. And in fact, I'm going to try and make it as elementary for you. I'm not going to use any cohomology. I'll just try to formulate it in terms of elements. So fix an affine variety over the p-adic integers. You write it as a finite extension of ZP adjoint x1 through xn. You can certainly always do that. So then the theorem says that there exists this finite extension, a further finite extension R to S. So this is the analog of the finite cover that showed up earlier, with the property that any relation amongst the xi's in R mod P becomes trivial in S mod P. So trivial over here means a linear combination of sort of the obvious relations. The obvious relations being those of the form xi xj equals xj xi. And so what this is saying is that these x1 through xn become a system of become a regular sequence on R mod P. So they're sort of as nice a collection of elements as possible. And you can rewrite this in terms of local cohomology, and then it will end up looking a lot similar to what I had on the previous page. But here's another conceptual reformulation of the theorem, which I like quite a bit and is actually important to the method of the proof, which is the following. So you set R plus to be the absolute integral closure of R, meaning the integral closure of R and the algebraic closure of its fraction field. And then this theorem, essentially by passing to the direct limit, will tell you the following statement. So it says that R plus mod P is a Cohen-Macaulay module over R mod P. So Cohen-Macaulay modules over commutative rings are some of the nicest class of modules one has to work with. And what the theorem is saying is that R plus mod P is one of these modules. And so the existence of such modules over commutative rings was a big open question in commutative algebra that was only solved last year via rather indirect arguments, or 2 years ago, sorry, by rather indirect arguments by Yves André and Ofer Gaber. And so this gives you a much more direct construction of those modules. And so, okay, I'm running out of time, so let me just quickly make some remarks on this and mention one application. So the remark is that this theorem was previously almost known for n at least and at most 2. So almost here is in some technical sense of almost mathematics, which I'm not going to explain. This is due to the work of Heitman. And the second remark is a sociological one, which is that experts had talked about this theorem for the last 30 years, but as far as I can determine, no one ever explicitly conjectured it in print. So it's kind of a funny state of affairs. And my very last thing I wanted to say was an application of this result, or this set of results, in birational geometry. So this is similar to the applications of Kodaira vanishing in classical birational geometry, which is to the minimal model program. And similarly, once you have this version of Kodaira vanishing in mixed characteristic, you might hope that there's a similar application to birational geometry in mixed characteristic. And that's what happens. And so here's kind of one way to summarize the statement, which is that one can run the minimal model program for arithmetic threefolds with residue characteristic at least 5. And so there are some technical reasons why we need p at least 5, but this is the statement in birational geometry one gets out of it. Okay, so I'm out of time and I'm going to stop here, but I will leave you with one slide containing a bunch of results proven recently using prismatic cohomology, which really surprised me because somehow the statements did not involve any prismatic cohomology. Thank you for your attention.